this is you. I didn't have your name on it.
Oh, sorry.
Is that yours?
Yes.
Yeah, okay. Thought so. Make sure I put the right grade on here. Andy. How is mine? Actually, I found your homework one, so it was in there. It was just one page, so I didn't see it. I think you submitted it late. Right?
Yeah.
Okay, I just want. Oh, I'm sorry, I don't know what you're both. You're sitting right in front of me, that's the problem. Should have been sitting in the back. Oh. Sorry. Okay. Sorry. Okay. Okay. Well, I'll get your name right. Okay, so let's continue discussing coherent states and from the last class. So we introduced these states and their statistics. So we define them as eigenstates of the annihilation operator, and their photon statistics, which we derived. There's a probability to be in the nth Fock state, which is alpha projected on n amplitude squared, is given by a Poisson distribution with a magnitude of alpha squared, right? So that is the average value of n for this state is alpha squared, and the variance delta n squared is equal to also the average value, which is also alpha squared. Okay. So this is the example now of Poisson statistics. We already saw examples of super Poisson statistics and sub Poisson statistics with the examples of the thermal state and the Fock states. Okay. We also discussed the picture in the x and p plane for these states, right? So x versus p. What does it look like? What does a coherent state look like in the x and p plane? A blob. A nice circular blob, right? And with the center is at a distance alpha from the origin with an angle phi, which is given by, of course, the eigenvalue alpha for this state. Okay. And we can even ask if the uncertainty in the n, that is in this distribution delta n, right, is related obviously then to the size of the uncertainty of the blob in this radial direction, right? And similarly, you could ask, is there some uncertainty in the phase, right? Clearly, there is some uncertainty that you could specify. This sort of gives you a number phase uncertainty relationship for a coherent state, okay? So starting from the uncertainty relationship for x and p, you can then derive an uncertainty relationship for the number delta n and the phase delta phi from this pictorial diagram. Of course, it's a little harder to justify it from the Heisenberg principle because it's hard to define a phase operator in quantum mechanics. So even though it's easy to define sort of a number operator, it's harder to justify a phase operator in quantum mechanics. So, and the reasons for that are many, but I won't go into those here. I can give you more reading if you're interested in that, about number phase uncertainties and things like that. From, like if you had a number phase uncertainty commutator, like if there was some operator phi hat such that n hat phi hat was something, right? Then you would immediately derive using the Heisenberg principle such a relationship, right? The problem is because of the multiple valued nature of phi, these operators cannot be defined. So that's, but there are some workarounds for this. I won't get into that, as I said. It's a more advanced topic in quantum optics. So what I want to derive now is that, but clearly you can see that you can operationally define some uncertainty in phi by just looking at this blob and defining some uncertainty in the sort of the in the position of this blob and in the angle of this blob. You can define an uncertainty for the phi, and you can define an uncertainty for n, of course, and then you can derive an uncertainty relation between n and phi out of that. Okay. So another important aspect of coherent states is they can be generated from the vacuum. So the state alpha, which I let's see. Okay, sorry, I didn't write down. I wrote down the. But if you also go back to the earlier class, I showed you that the state alpha can be defined as e to the minus alpha squared over 2 times alpha over n square root n factorial n, which is of course just what I wrote down here in terms of the number statistics, right? This is the expression for alpha in terms of the number states n, but we can also define now an operator d of alpha, which will be familiar to you from our very first week when we talked about quantum mechanics, which is this operator, which is called the displacement operator. Okay, and you can show that d of alpha on acting on the vacuum generates the state alpha. So that's why this is called the displacement or shift operator. So this is the displacement or shift operator. Okay, and if you want more details, you can look at Meister and Sargent or any other book like Scully, page 310. There's more details. So I'll just quickly go through a proof that in fact this is true. Okay, that d of alpha acting on the state 0 equals alpha. You may recollect this operator from earlier. Do you remember what this was? Where this came from? Where you've seen this operator before? I mentioned like the very first week or maybe second week of class that we discussed this operator. What problem did we discuss in class? Forced harmonic oscillator. Exactly. So as I'll show you in just a minute, then forcing a harmonic oscillator essentially allows you, if you have a harmonic oscillator in its ground state, that's what this is saying. Driving it with this operator, which we know comes from the time evolution of a driving term on the harmonic oscillator, produces a coherent state, which is why we always say coherent states are like a very classical state. If you just classically drive a quantum oscillator in its very ground state, with some forcing term, some external force, any external force that typically could act on the oscillator in time, which is proportional to say its position, right? That drives it with its position. or even with the momentum, as we showed you in the class, it could be a damping also. There could be some damping or other terms involved. All of those, a damp-driven quantum oscillator will become into a coherent state. Okay, and that is the statement which is here. And in fact, now we have shown what that coherent state looks like. Okay, so to prove this, we use the result from the Baker, Campbell-Hausdorff lemma that e to the a, e to the b, or in this case, e to the a plus b, I guess, is what we care about, is equal to e to the a, e to the b, e to the minus ab divided by 2. Okay, this was one of those things that you proved in your assignment, where, of course, we have assumed that a, b equal to 0. Okay. So A and B, A or B commute with its commutator. Okay. So which is certainly true for our situation with A and A dagger. So if I now set A equal to alpha A dagger and B equal to minus alpha alpha star A, right? Which is exactly what this situation is, then this is e to the a plus b, right? That's our displacement operator. Then we just need to work out the commutator, which is very straightforward, which is just minus alpha a dagger, alpha a star, alpha star a, and that is of course just minus alpha squared. Okay? Oh, plus alpha squared, because this is a dagger a. An a dagger commutator with a is minus 1. Okay. All right. So when I substitute that back in here, I get that d of alpha can be written now as e to the minus alpha squared over 2, right? Times e to the alpha a dagger times e to the minus alpha star a acting on the vacuum, right? So d of alpha acting on the vacuum produces can be written like this because of this identity that I just proved. Okay, and you can see what is the action of this operator e to the minus alpha star a acting on the vacuum. E to the minus alpha star a acting on vacuum will be? Will be the vacuum. Okay, good. Because e to the minus alpha star a has the identity plus terms involving higher powers in a, right? A squared over 2 factorial, etc. And any a acting on the vacuum will give me 0. So only the first term, the identity part, survives. So that is just the vacuum again. So this result now is going to be pretty simple, acting on the state 0. And so let me continue on this side. I will keep that because it will show you in a second that these are identical. I'll leave that over here as well. So continuing from there, e to the minus alpha squared over 2 times, now this e to the alpha a dagger acting on the state 0 can now be expanded, summation n equal to 0 to infinity, alpha a dagger to the n divided by n factorial acting on the state 0, and now a dagger of n acting on 0 will give me a square root n factorial acting on the state n. So this becomes e to the minus alpha squared over 2 summation n equal to 0 to infinity alpha to the n divided by square root n factorial acting on the state n, right? So that is identical to this earlier expression that we had derived for the coherence state. So therefore this is the coherence state alpha, which was what we were trying to show. Okay. So now let us ask So this shift operator gives us a nice interpretation of how to generate a classical coherent state. We already talked about it in the second week of class that the shift operator will result when we unitarily, when we consider the time development of a harmonic oscillator that is being driven by some external forcing term. And we can also see that by looking at the interaction between a classical dipole. Okay, here's a classical dipole D dot E. Okay, acting on a quantum electric field. Okay, so the quantum electric field is basically A e to the minus I omega t plus A dagger e to the I omega t, right? That's what we already showed when we wrote down the electric field, the quantum electric field in the last class. It had these terms, plus e to the ik dot r, I'm assuming r is equal to 0. So we position the thing at 0, and then we position the classical dipole, some antenna, for example, that is just having some current or something going through it, that we'll just write as d naught cosine omega t. Okay? So when I write that, and now when I expand cosine omega t, this is there's a minus sign, d naught e to the minus I omega t plus e to the plus I omega t times then this here times a e to the minus I omega t plus a e to the plus. So if you have such a Hamiltonian, then we can immediately use the RWA, the rotating wave approximation. We'll get terms with e to the minus 2I omega t, e to the plus 2I omega t, those we will neglect, okay? And then this guy will be essentially in the RWA, rotating wave approximation, as just minus d naught e naught divided by 2, so there's a factor of 2 here, okay? Times A minus d naught e naught divided by 2 A dagger, right? And then the propagator, the time propagator for this guy, which is now time independent, so I can just use the unitary time development operator to be just e to the minus IHT over h bar, right? So this is a time independent operator, so I can just simply write that. So that becomes e to the I d naught e naught over 2 times t times A plus I d naught e naught over 2 times t times A dagger. Okay? So this term over here is minus alpha star, and this term over here is alpha. So we get e to the minus alpha star A plus alpha A dagger. Okay? And if you go back and look at your notes from the second week or so, you will see that we had a similar result for the terms that are sitting in front of the A and the P, except that was much more generalized. We allowed you to even have time dependent forcing, right? We had a time dependent forcing f of t, and we just had to calculate its Fourier spectrum and so on. I skipped all those steps here just to show you, this is what will happen if you have a classical dipole which is driving a quantum field. Where would you see this? For example, suppose you take, how can we get a quantum field, right? Well, obviously one way in which we can get a quantum field is when we have some cavity which has a single mode, right? Some kind of electromagnetic boundary conditions that has a single mode that inside it, and then we allow the single mode to be completely empty, right? And then we can put in an antenna, for example, simple dipole antenna or something, and drive it on an atom, and we can drive that atom, and then the atom will produce essentially this classical state of the light because it will produce this time development of the operator. Okay. So then this guy then essentially what I'm saying is D, the shift operator with the alpha given by I d naught e naught over 2 times t. So the value of alpha is basically proportional to the magnitude of the dipole moment, magnitude of the electric field, and the time. Okay, so in this picture, that as time keeps going, alpha will keep increasing. Okay, so of course this has no damping built into it. Okay, the cavity is assumed to be perfect. The electromagnetic field doesn't leak out anywhere, doesn't dissipate into anything, etc. Later on, we'll come back and see how to address the situation when the cavity actually has some damping in it. Okay, but this is just a classic or simple picture of why, when you drive a cavity with a classical dipole, like for example an antenna or something like that, it's going to produce a coherent state from that situation. Is this clear to everyone? How coherent states work? These are very important, obviously, because almost all the time you're dealing with things like lasers or some kind of oscillator that's being driven by some external system, and then very typically, unless you're very, very careful, you'll end up with a coherent state, right? Almost inevitably, all of these will go into a coherent state. That is the standard thing that happens. So understanding their properties is very useful and important. And as we saw, even thermal states, once there are many, many modes of thermal states, as we saw last time, those guys also look like coherent states in terms of the Poisson statistics. But there will be a way to distinguish them, as we will see, from higher order correlation functions. That will be the next subject, or maybe not the next one, in a little bit. Okay, so we have talked about coherent states, and some of this is like, hopefully not new for you, especially with the shift operator. We looked at the behavior of the shift operator and how to get it before, and I'll give you a couple homework problems on the shift operator and so on. Now I want to examine one other type of state, which is the squeeze state. So you already seen that the displacement operator, which I erased it, but it has a term that's linear, that is e to the some constant times a plus e plus some other constant times a dagger, right? So it's linear in a and a dagger. Okay, right? The squeeze states come about from a natural generalization of this, which is that you now take this coherent state and you operate on it with a term that has a squared and a dagger squared. Okay, those would be the squeeze states. Okay, so the first I introduce them in this way, which is that squeeze state So just as coherent states are generated by taking d of alpha, and as I showed you d of alpha, this was basically, I took d of alpha and operated it on the state C, right? And that's what I showed, that's the coherent state. So S of psi is equal to e to the half psi a squared minus half or psi squared a squared a dagger squared. Okay, where the psi again, or psi, I can never say it right, is some r e to the I phi is the squeezing parameter. It's a complex number which is the squeezing parameter. When S of the squeeze operator acts on a coherent state alpha, that produces squeezed coherent state. And for example, you could also look at things, so just like the alpha, this value of alpha can be anything, and it's a complex number, right? Alpha is a complex number which is parameterized by its amplitude and its phase. This amplitude and phase could be 0, right? So if the amplitude and phase is 0, that's a vacuum state, of course. Okay, but it's a coherent vacuum state, right? So, but in this case, it turns out this vacuum state, if alpha is 0, then that's just the vacuum, right? So S of psi acting on the vacuum, right, is called the squeezed vacuum. And the reason we have these terms is, of course, it means that even though the amplitude of the electric field is 0 in the vacuum state, it has some fluctuations. Okay, right? Because as we saw earlier, the vacuum state has some fluctuations which are due to the vacuum fluctuations, right? So that delta E squared is basically, we have to evaluate it. Okay, and this state here is basically going to create pairs of photons because it has terms which are A squared and A dagger squared in it, so it will always create and annihilate in pairs, okay, of photons. So that also gives us a clue of how to generate such a state in a Hamiltonian picture. But before I do that, let me just sort of show you what these states look like in the x and p and in the time domain. Okay. Again, if you have more, I can assign more reading about this, and I'll give you a homework problem on proving this result. Okay? I'll give you the general idea of that today, but you will have to prove some of the mathematical results in the homework. Okay, so let's think about what the coherent states are, right? Let's say, in fact, we take a coherent state which is primarily a block along the x-axis, right? Then we know E is equal to summation of x hat cosine omega t minus p hat or plus p hat sine omega t. Okay, that's how we wrote this in an earlier class. We showed that this is indeed true. So when x takes on some values and p takes on some values, basically what we have to do is sum up all of those terms in this picture for this operator, right? For the state E. Okay. So what does E of t look like in this coherency? Right? It has cosine and sine terms, right? And each of these cosine and sine terms in this guy will have some amplitude, right? And they'll be out of phase if they have some p in them. Okay? So basically it will have some value of x times cosine of omega t plus some value of p times sine omega t. And you have to add up as many of these as there are in this x and p block, right? That's what a coherent state will look like in time, right? As we let the time evolve. So if I let time evolve for E of t, then basically it's going to look something like I don't know how well I'll sketch this, but you'll hopefully get the idea. And of course it has some fuzziness because of the fact that these x and p have some uncertainty in this block, right? So the amplitude and the phase are slightly uncertain, okay? Exactly the value at any time, and exactly, for example, where it becomes maximum or minimum, the phase are uncertain by some amount. This is the coherence. So this is the time domain picture for the electric field in a coherence state, okay? I should mention that so we also remember that delta x delta P for a coherent state is exactly equal to 1/4, right? So we must always satisfy the Heisenberg uncertainty relation that delta x delta P is greater than or equal to 1/4. Okay. All right, so this was the coherent state. Now imagine a state, okay, which is squeezed by the squeezing operator along the x direction. So we make the uncertainty in x smaller, and we, of course, to satisfy the Heisenberg uncertainty relation, we have to make the uncertainty in P larger, right? So for example, here delta x equals half, delta P equals half. Here, maybe we made delta x squared equal to 1/16, and delta P squared equal to, say, 1. Okay? So delta x delta P still satisfies 1/4. Okay? So this is the squeeze state in the x direction. So the uncertainty will be minimized because this guy is cosine of omega t. The uncertainty will be minimized when the contribution comes mostly from x, which will happen whenever cosine omega t is largest. Right? So whenever cosine omega t is largest, the uncertainty in the electric field will become the smallest. Because that's when the contribution comes mostly from the x part of the electric field. So in the same picture, basically, whenever I start to get up to this guy, my uncertainty suddenly reduces. Not suddenly, it's reducing all the way, but it especially becomes very small. The amplitude, sorry, I'm trying to draw in the same time domain. Right? Oh, sorry. So here you can see the uncertainty became almost zero in the electric field because it's very small. It's delta x squared is 1/16. Okay? And then and so on. Okay? Sorry, this is not very, perfect. Maybe I can even sketch it out on Mathematica or something and show it to you guys next time. But this is the general principle of it. Okay? So again, it still satisfies delta x delta p is equal to 1/4, but because the uncertainty has been squeezed in the x direction, whenever the cosine part becomes largest, then that's where the uncertainty in the electric field also gets the smallest. Okay? And similarly, we can also look at the other side when delta x delta p is squeezed along the other axis, along the p direction. So I'll just erase this one and just draw it over here. So now delta x delta p is now squeezed on the other side. So we get that it's a bigger blob in the x direction and a smaller blob in the, so delta x squared is 1, delta p squared is equal to, say, 1/16. Okay? And then you can basically take Mathematica and make it, add up all these amplitudes for the wave and look at what happens. The electric field now will be, it'll now have the largest uncertainty in the amplitude and the smallest when sine omega t is largest, so you'll get something like this. can see that the uncertainty becomes very small when the sine omega t. So this is the sort of the variance in the amplitude, and the variance in the amplitude clearly gets much larger, right? So now the whenever we approach a point where sine omega t's contribution is largest, which will be near pi over 2, 3 pi over 2, and so on, that's when the uncertainty becomes the smallest, okay? Because of the lower uncertainty in t. Okay, if you're not convinced, we can you can sketch it out for yourself in Mathematica or something, and I can maybe share that in the next class or online. I'll put it on the course. Okay, so I said that the squeezing operator is able to generate the states from the coherent states. So in fact, we will show that a general squeezed state looks something like this. So in this case, the squeezing, as you could see, right, it was either in the x direction or in the p direction, but you could have a combination of both of those, right? And in fact, that then you can derive that the so this is x and p, and then a generalized state which will look something like this. This is the blob, right? Sorry, here I didn't. This is the blob in both these cases, right? For the x and p, and you can show that the most general state looks something like there's a new operator x1 and x2, which is now a combination of x and p, okay? And this new operator x1 and x2 has some uncertainties, delta x1, and delta x2, okay? And these delta x1 and delta x2, their values are given by e to the minus r over 2 and e to the plus r over 2, where these, oh, sorry. I had to check this. It might be minus r over 2 and the plus r over 2, I think. Okay, I'll check that. I can't figure out whether the 2 is up there or down here, or down in the denominator. It doesn't matter. Oh no, it has to be the denominator. It has to still satisfy the Heisenberg. So delta x1, delta x2 is still 1/4. So it still satisfies the minimum uncertainty product, but each individual values may be squeezed by different amounts by this factor r. And the r comes from that squeezing parameter psi, which has some value r e to the I phi. Okay, so that's where this comes from. Okay, and you will show in your homework that this x1 and x2 are related to that r and phi through this relation. So the phi there that comes into the squeezing parameter is how much you have to rotate the axis x to get the x1 and x2 from x and p. This is phi over 2, phi over 2, and that gives you the definitions of A and A. So I'm not proving this, but you will show it in the homework. It's fairly not too hard, I think. Some algebra, quite a bit of algebra. You will get. Okay, so that's basically about squeeze states. So before I move on, I want to ask the physical question. So we've discussed the properties of squeeze states from the squeezing operator, right? That's a mathematical perspective. And we've also discussed what that does to sort of the amplitude and the phase of the electric field that you're looking at, okay? But now we can ask, where do they come from? How do we generate such squeeze states, right? How do I, remember when I told you about coherent states, I was very clear about how we can generate coherent states. I said you take a classical dipole and you drive it in a cavity, for example, like an antenna, then that's going to generate a classical coherent photon field. Okay, coherent state of the photon field. We also, if you go back to the very first lectures, we discussed about how to generate coherent such kind of states from a classical oscillator that we just force with some external field, external force. Like you take your X and P, like a classical mass spring system, you apply some force on it, and then that force will automatically create a coherent state. Well, it'll make the time development operator be this displacement operator, and that displacement operator will then generate coherent states. So where does the squeezing come from? It's actually pretty straightforward now to see that because of the form of the squeezing operator, which I erased, but I'll just write it over here again. S of psi is equal to e to the half psi star a squared minus half psi star a dagger squared. Okay. We know that now, just like when we did with the harmonic oscillator and a classical dipole that was driving the field, we now need to have terms in the Hamiltonian. For the coherent state, we had the term d dot e, right? And the d was just d cosine omega t, and the e was just a plus a dagger with the relevant e to the I omega t and minus I omega t. Okay, so that gave us coherent states. What we're going to need for the Hamiltonian in the squeeze situation is something that goes as some a squared plus a dagger squared. Okay, so we're going to need some Hamiltonian, this G star. Okay, so this is the form of the squeezing Hamiltonian. It's going to need terms that have a squared and a dagger squared in them to generate these squeeze states. Okay, just like we had in the coherent state, we had terms that were linear in a and a dagger, which was easy to generate from just say a dipole element, right? The dipole approximation d dot e automatically uses. This one is a little harder, okay, because this requires the a squared and a dagger squared. So, so I won't prove this right now, but we can come back to it once we have looked at some other states, some other interactions of the atom in the field, which is that if you take an atom, okay, some atomic state, and I drive it with some classical field, okay, E naught, which is I call the pump field, okay, E naught is a pump at frequency mu naught, okay, and then I look at the evolution of the system. Well, there's a probability that instead of emitting back down to the ground state at the same frequency as the pump laser, that this can produce two photons of two different frequencies. Okay, nu1 and nu2. Obviously, this is a very weak term because it doesn't happen all the time, right? But it's still energy conserving because nu1 plus nu2 add up to give you nu naught. Okay? And this process especially becomes strong if there is some intermediate state that is nearly resonant with this one of these photon states. Okay? And I can derive for you in that situation that there is this term G, this G that we were talking about is proportional to the pump amplitude, right? Or the pump power, omega naught squared, omega naught. I'll explain these terms in this way. I haven't derived this result, but I can show it to you later, or maybe I can give you a handout on this, because it uses the same approximations for the three-level system that we derived earlier, and it basically you have to derive what happens to the dynamics of the state. Okay, so So there are several terms here. There's a big delta, which is the detuning from the excited state. There is a little delta, which is the detuning from the intermediate state. Okay, and GC is the coupling here between the field A1 and this dipole moment 1, 3, for example. This is 1, this is 2. This is one such possible scenario where you can generate such a coherent state. Okay, sorry, squeeze state. Okay. The point of this is just that this indeed is a allowed Hamiltonian in this situation, where you essentially eliminate the state 2 and then describe the dynamics in terms of the state between the two states, nu 1 and nu 2. So the nu 1 and nu 2, instead of being classical fields, now have quantum properties, A1 and A2, right? And then you can get exactly this term. And if, of course, when you have degeneracy, which is when nu 1 is equal to exactly nu 2, then this becomes exactly A squared and A dagger squared, which is when nu 1 equals nu 2, then nu 0 equals some 2 times nu 1, for example, right? Which is what this is described. So this is called degenerate parametric down conversion, okay? Or two photon absorption and emission. There are various names for this process. In nonlinear optics, for example, this is a common process where if you send a pump beam into a nonlinear crystal, then you can have the pump beam keep propagating, of course, unchanged, or you can have part of the pump beam being converted to two photons of lower frequency. Okay, and this is a typical situation in which this may happen. If the material is made of atoms, then this would be one situation. There are other situations with crystals where you may have some nonlinear susceptibilities. We've also discussed how one can have nonlinear susceptibilities when we looked at the behavior of a two-level system under the action of some strong pump beam. We saw that there is indeed automatically nonlinear behavior of the dipole moment, right? Way back when we talked about the interaction of atoms with semi-classical fields, the dipole moment of an atom that's being driven by some strong pump beam automatically has terms at various frequencies. That gives rise to a nonlinear susceptibility, which could also give rise to these kind of behaviors. Okay? And that's a typical example. For example, in superconducting circuits, they have such situations where if they drive their two-level atom or nearly two-level atom with a strong pump, then the susceptibility has nonlinear terms at multiple frequencies, and then they can interact with those multiple frequencies with a cavity, and that cavity will then have degenerate or non-degenerate even parametric down conversion sources or parametric amplifiers and so on that you can create, and parametric oscillators and so on that you can make from this kind of an interaction. Okay, and you can see also that kind of interaction, as we just discussed, will generate our kind of squeezed states as we just described. Okay, so this is all a very rich area of physics right now. Initially, this could be some reading that you guys can do, which is to read about how the initial experiments in the squeezed states worked with precisely these kind of systems. So people worked with nonlinear crystals. They worked with also like atoms in some kind of cavity, in discharge tubes, etc. And they showed that you can generate these kind of nonlinearities, and then you can actually obtain squeeze states. And so, I would say in the 80s and 90s, this was a very, very important area of research in optical physics, where people were very interested in generating squeezed states of light. And even into the 2000s, I feel like it's sort of maybe died down a little bit in the last 10 years or so in the optics community. But in the superconducting and microwave domain, it has become a very hot topic again. It kind of like learning quantum optics, you pretty soon see that there's a lot of overlap between all these different regimes. And so these squeeze states have become, and for example, then people realized also that you can use these kind of interactions to generate photons that are entangled with each other. And that became a whole separate area of like quantum information research. So understanding this Hamiltonian, understanding the effect of this on like different kinds of fields is actually very an interesting direction of research even now, and something that some of you may want to look into for your end of term papers, okay, and projects. So in the last parts of this, I want to come back to some of the things I said I would discuss, which is how do you characterize the states of photons when we don't know, for example, the interaction or the Hamiltonian. Like suppose you are given some source of photons, okay? And we already discussed how photon statistics doesn't always reveal everything about the actual state of the system. Like for example, you may have a hard time knowing if some system is in a coherent state, if it is in a multi-mode thermal state, if it is in a, what if it's in a sub-Poissonian state, etc. All of these things are sometimes hard to know. So we want to come up with a systematic approach to understanding all of these states of light and how to characterize them experimentally in the lab. And we also want to look at, for example, what these kind of states or what these kind of experiments could tell us about quantum information processing. Okay. So I mean, this whole area of coherent states by itself also has applications in things like quantum key distribution. People are very interested in using squeezed and coherent states for quantum key distribution over various types of channels. So if you don't know what quantum key distribution is, we'll come back to it later on in the term. So, but effectively, like understanding these states and understanding the properties of these states is a very important and for research as well. So let me talk about how to characterize these states. So far I've told you about how these states might be created. We've talked about, like, if I took a dipole and connected it to some cavity and drove the dipole oscillator antenna or something, I'll create a coherent state. But we've not talked about what you can do with the coherent state once it has been created. Well, you all know this in the lab, that you can take a laser beam or something, you can put it on like polarizers, you can put it on like phase shifters, you can put it on beam splitters, various things that you can do to this state of light. So the first sort of things that we want to discuss are linear optical transformations, and this will then help us to understand how to manipulate the states of light. And this, in fact, is its own branch of quantum information as well, which goes under the name of linear quantum computation, or linear optics quantum computation, photonic quantum computation, etc. Okay? So the first sort of thing that you could imagine doing and we'll be working sort of in a Heisenberg picture for this, because we are now, as you have seen, for quantum states of light, we are working mostly with the operator A and A dagger, which generate these states. So a phase shift operator on a state is basically one that makes this state go from A to A times e to the I phi. So under this operator, coherent state alpha will evolve. So this is the phase shift. Will evolve as alpha e to the I phi. Right? So that's a simple operator. And what do I mean by linear, by the way, here? Is that this is independent of the magnitude of alpha, right? So the phase shift operator will do the same operation independent of the magnitude or the intensity of the light. So maybe I should write that. This is independent of intensity. Here, for example, the squeeze state is generated based on the power of the pump beam, right? So this would be a nonlinear optical transformation, okay? Whereas this is a linear optical transformation. The next one is a beam splitter. So in a beam splitter, what we can think about is that the incident mode that is coming in, A1, right, is converted to two different modes. Okay? So you have an incoming mode of the electromagnetic field, and then you have two outgoing modes, A3 and A4. Now, because of course we have to worry about quantum states of light, even if you send in a laser on this side, you can have a quantum state of light coming in from the other side. Okay? So we typically write a beam splitter transformation as a transformation between these A1 and A2 modes going into the A3 and A4 modes. So these are the annihilation operators for the single modes which are coupled by the beam splitter. Okay? So it's still single mode physics. Well, maybe it's two mode physics now. Okay, so we went from single mode physics, which is all we were looking at until now, right? We just had one mode of the electromagnetic field. Now we're doing two mode physics. Okay, so there's a mode here and a mode here, which couples into this mode and this mode. Okay, and what is the transformation? Well, it's a matrix. So A3 is equal to T13 times A1 plus R23 times A2. And A4 is equal to R14 times A1 plus T24 times A2. And because of the properties that this matrix must satisfy, that is that this matrix U, which is, and we are assuming that this is a lossless beam splitter, but as you can see, this T13 is just the amplitude for transmission from 1 to 3, and then R23 is the amplitude that from A2 I go into the mode A3 by a reflection at the beam splitter. So that's how A3 can be created, and similarly A4, that is this mode, can be created either by reflection from 1 into 4 or transmission from 2 into 4. Now in the microwave domain, these kind of matrices, these are like S-parameter matrices, right? So if you have done any microwave optics, then you look at this as like a two-port device, the beam splitter, and you can think of the two-port device as having some matrix that relates the input to the output parameters. Okay. Okay. So these are lossless, or these are lossless beam splitters. Then we must have U dagger U equal to identity operator, right? I'm trying to remember, is the, can you remind me, you guys from Hatridge group, so is the S parameters, it's more like you have two guys coming in, you have some, this is the S parameter, right? S parameter, so it's like you have input mode going in, 1,
Yes.
and then you have S11, right?
Yes.
For the, oh sorry, that's, wait, which is S11? Is it 1 going back into itself?
The S matrix only have 2 ports.
Oh, S matrix is 2 port.
Yes, yes.
Sorry. Okay, that's maybe what I made a mistake. Okay, then this is just like a transform matrix or something like that. Okay. All right. So once you put this back in here, you'll find very quickly, right? So to satisfy this condition, that you will need to have these two relations satisfied. Right? Just by substituting, you'll get all of that. And you can see that there are still several choices possible for even for the situation when you have 50-50 beam splitter. For example, you could choose the phases of these R's and T's in different ways to satisfy this condition. Okay? And so there are typically two different conventions that are used in the literature to satisfy the unitary condition. They work. You may also ask yourself, like, okay, when do I get these two types of beam splitters? It depends. For example, in the beam splitter, you might have dielectric beam splitters, right, which are obtained by some kind of AR coating on some piece of glass. Or you may have like half silvered mirrors, which are basically like taking a piece of glass and coating it on the back with like some metal, for example, some thin layer of metal. Okay, and because we know that metals have a different Fresnel coefficients than say dielectrics, then you can have different phases for the input and output electric field amplitudes that come about, and that can then affect the type of beam splitters that you're choosing to use in the lab. But we can always typically make some kind of transformation and say that we will consider two types of beam splitters based on this that have to satisfy these conditions, and not worry too much about exactly how you may realize such beam splitters. Okay? So the two types of beam splitters that are seen in the literature typically is one is called the symmetric beam splitter. And again, you can look on Meister and Sargent, page 480, for these kind of definitions. But the different conventions are that we choose say T13 equals T24 equals some T. This is the transmission. Okay, transmission from 1 to 3 or 2 to 4, and those are equal, right? And then we choose that R23 equals minus R14 star equals I times R. Okay, so then the reflection comes with a 90-degree phase shift at the beam splitter. Okay, so now if I want to write this matrix for A3, A4, it is T IR, IR, T times A1, B. Okay? This is the symmetric beam splitter. And then we can also have what we call the real beam splitter. And I'll just write the matrix. It is just T, R, R minus A. Okay? So that comes with a 180-degree phase shift between transmission from the mode 1 to 3 and then the mode 2 to 4. They have a 180-degree phase shift between them. Okay. And that is actually well known from real beam splitters, that are in the lab, that you can observe this phase shift. For example, in a Michelson interferometer, you can observe that, for example, where you expected the central fringe to be, say, bright for zero path length difference between the two arms, the central fringe will actually be dark. This comes about because of these kind of phase shifts at the beam splitter between the two arms of the Michelson. Okay? Or even the same thing with Mach-Zehnder interferometer. So there are various situations where this actually makes a physical difference to what is observed in the experiment. So you do have to keep track of it. Okay. Alright, so the next thing I want to talk about is photo detection and correlation functions. Okay, so let me just make sure there's one other thing. I described all this in the Heisenberg picture. You can also ask what happens in the Schrodinger picture, because we are thinking about states of the field. Until now we were talking about, you know, the coherent state, the Fock state, the thermal state and squeeze states. What can I do to go from this picture, which is the Heisenberg picture, to the Schrodinger picture? Okay? So it's not very hard. So once again, we just use the operator U. So for example, I'll just give one little example here, and then you can look at some other situations on your own. Let's see. Let me just continue. Okay. So the Schrodinger picture. The vacuum is the same on both sides. So we have so now I'm talking zero vacuum coming in here and zero vacuum coming in here. Well, that will still become 0,3 and 0,4. Okay. And since A2 dagger, in this case, is let's say we took this situation over here, which is T IR IR T. So we have that. Well, I guess I'm trying to invert it here. Hold on a second. Sorry. Okay, I guess what I was trying to do is, I want to now consider the state 0 in mode 1 and 1 photon in say mode 2. Okay? So here I have 0 in 1 and 1 photon in the mode 2. We are asking what will happen to this state now, coming out of the beam splitter. Okay? So to do that, I need to know what A2 is in terms of A3 and A4. Okay? So I have to basically invert this matrix. Okay? So A2 dagger, because this of course is 0 in state 1 and A2 dagger on the state 2, right, on the vacuum, right? And so A2 dagger is simply for, and I'm assuming a 50-50 beam splitter, is A4 dagger divided by root 2. We can have that the operation of the beam splitter on this state 1, 2 becomes 1 over root 2 of IA3 dagger plus A4 dagger acting on 0, 3, 0, 4. Okay? Right? So what I'm saying is 0, 0, 1 is equal to 0, 0 with an A2 dagger on it. And A2 dagger is IA3 dagger plus A4 dagger, which operating on these modes 1 and 2 produce the vacuum 0, 3 and 0, 4, but plus they also have these other terms in them, which is essentially, so A3 acting on 0, 3 produces the state 1 in the third mode times 0 in the fourth mode plus 0 in the third mode and 1 in the fourth mode. Okay, plus some factors of 1 over root 2. Not too important. The point is, now the single photon that came into the beam splitter, right? So we had a single photon state coming into the state A2. You see that the single photon state 1 is either in the state 3 or in the state 4 in this final situation. In fact, it is path entangled, as you can see, because the output state cannot be written as a product of the inputs of the two individual states. Okay, if you don't know what that means, I'll come back to it later. The point is that the initial photon in one mode is not like it is half the time in one or the other of the output modes. It's always either in mode 3 or in mode 4. So So if I put a detector here, right, and I put a detector here, okay, you'll never get what we call coincidences between these two detectors. The photon will either click here or here. You'll never get a situation where both detectors click. Okay? Of course, if you took a classical state, like a coherent state, right? If you take a laser, for example, and put it on a beam splitter, you expect 50% of the intensity is over here, 50% of the intensity is over here. Okay, and you will see coincidences, basically, because the two guys, there will be many times where there are photons hitting both of the detectors. Okay, that's because a many photon state is fundamentally different from a single photon state in this range. Okay? That is just the first example. We can also calculate other things. For example, you can do this for the coherent state. Okay? Maybe I quickly sketch this out. Okay? Let me do it for the coherent state as well. That might be interesting. Oh, I'm out of time. Okay. All right, we'll continue this in the next class.